Right, at GCSE level, you required to do certain tasks or constructions using just a straight edge and compasses, and sometimes a set square as well. For example, how do you construct a parallel line? How do I construct a parallel line to that? Well, I'll need to use a set square for that. Straight edge, and I'll slide the set square along the straight edge. Well, sorry, I'll try and start again. Okay, so these lines now are parallel, or close enough, taking into account my small errors there. But you get the general idea. Next task would be, how do I split a line up into, say, three equal parts? Okay, so I don't know what this line, how much this line measures. I mean, obviously this straight edge does have measurements on it, but I'm assuming that I'm living in an idealized situation where this is just a straight edge, no measurements. So I have no idea how long that line is. How do I nevertheless split it up into 3 equal parts? Well, first off I draw a line off an angle like that. Then use my compass to mark off 3 equal lengths. I connect the end arc with the end of the line. Now the point now is to make two lines parallel to that. And that'll demarcate the what I want to, what I need. So yeah, as I say, it would be easier with larger instruments than what I've got. So there you are. That line has now been split up into three sections, each of equal length. Now, perpendiculars. How do I construct a perpendicular bisector to this? Well, I'd set my compasses to a greater length than half. Put it on one edge. I'll draw these. Typically you would draw these arcs very faintly, or as faintly as you need, but I'll draw them as thick as I can on here just to show the method. Construct a line between those two intersections, and there you are. That will intersect at 90 degrees, and that section there will be of equal length to that section there. So that's a perpendicular bisector. Well, just keep it there a bit longer. Right. How do I construct a perpendicular from an arbitrary point on the line? Okay, see there. I mean, that's not the center of this line, but I need to construct a bisector. So I would mark off equal points on the line itself, and then use those two intersections to do a similar procedure as before and mark off arcs from each. And hopefully this will go through A. Yep. So yeah, there you are. Goes through A, and that is 90 degrees. How do I mark off a bisector from the end? Well, I'll just choose an arbitrary point up here, and I'll draw okay, so can you see what I'm doing here? I've set the taking that as the center of a circle. I've stretched it as far as the point, the end point on the line. I'm going to just draw a circle with this. I now take that point there, where it's intersected, the circle has intersected the line, draw a diameter. I then take where the diameters intersected the circle and connect those. So that is now, that's the right angle, so that's bisecting the end of the line. And can you see why that is so? Basically, you've got a diameter here, and that diameter is subtending an angle on the circumference of this circle. And from what I've just said, a diameter will subtend an angle of 90 degrees, or a right angle, on the circumference of a circle. Next one is from a point, constructing a perpendicular to this line from a point outside, or not actually on the line. So first off, I'm going to draw two arcs on the line. Is this going to... no, I need to extend that line. And then I'm going to draw let's see if I can get my hand out of the way. I've drawn an arc from that point. Now I want to draw an arc from that point. And hopefully when I connect these it'll bisect the line at right angles. Yeah. So that's a bisector from P onto this line. Perpendicular. No, sorry, it's not a bisector. It's a perpendicular line from P. Perpendicular to the original line. Yeah, sorry, it's not a bisector. It's not a bisector. It's a perpendicular from P onto this line. Right, so that's lines. How can I construct an angle of 60 degrees? Well, I draw my line in originally. what I'm essentially going to do is construct an equilateral triangle, which is a triangle with all sides equal and all angles equal. So therefore each angle would equal 60. Now some people will draw a, well, I suppose it's 6 on one and a half and dozen the other really. Some people will draw a line in and then extend their compasses to that line and then draw and then proceed from there. What I'm going to do is I've taken the original line. I'm just going to mark off a point here. So I'm going to then do intersecting curves from each of these 2 points here and here. So you can see what I'm doing here. I'm constructing an equilateral triangle. That's the sort of base, if you like, and by virtue of the compasses being the same length as that, the actual if I conduct that with that, those sides will have the same length, so you'll have an equilateral triangle. Because I'm just trying to construct a 60-degree angle, I'll just I won't construct the entire triangle, I'll just do that, and that is 60 degrees. If I have some sort of arbitrary angle, how can I bisect that angle? I mean, I'll go through these fairly quickly. Hopefully it's fairly obvious or how these work. I mean, obviously because this is on video, you can sort of pause it yourself and have a think about it anyway, but it's hopefully fairly obvious what's happening here without me going into too much explanation. I want to bisect this angle, so I'll go like that. Can you see that? I've stuck 2 arcs on the original lines. I then use those intersections to construct another set of intersecting arcs. And there you are. That angle will equal that angle. That type of notation will indicate that that angle is equal to that angle. So that's bisected that particular original angle, and you could also, you know, if you've got an angle of 60, then you can get 30 by bisecting the 60, or if you've got a right angle, you can bisect that to get an angle of 45, and so on. Now, I'm not too sure. That's possibly all you need to know at GCSE level, possibly. You might... There is the idea of circumscribed and inscribed circles for triangles, which I could talk about for a bit, just for general... Well, it might be on the... You might find this on the syllabus. Because obviously when I'm saying GCSE here, there's I'm trying to include IGCSE as well and so on. So those are concepts that might be on the syllabus, so I'll talk about it anyway, and it's just of general interest anyway. The idea of a circumscribed circle of a triangle. I've already talked, although I probably haven't mentioned the name, I've talked about a circumscribed circle of a quadrilateral. If you... well, perhaps I will draw the circle first. Okay, this is obviously a very rough sketch. That would be a this would be a cyclic quadrilateral because you've got a circle around it touching all its 4 vertices, and that circle would be described as the circumscribed circle. And as you know, the property of a cyclic quadrilateral is that these angles, opposite angles, add up to 180. The technical term would be supplementary. If 2 angles add up to 180, they are supplementary. And not all quadrilaterals are cyclic. Things like squares and rectangles, and also isosceles trapezium are cyclic. I mean, they certainly definitely fill the criteria. Anyway, the square, has opposite angles adding up to 180, as does a rectangle. So it fits that criteria anyway. For an isosceles trapezium, it might not be immediately obvious, but when you think about it, because of the symmetry of the situation, that angle is equal to that angle, and that angle is equal to that angle. Should be able to readily accept that those angles are supplementary. That angle, those two angles there, do add up to 180. So they do at least fill the criteria for cyclic quadrilaterals, and yeah, they are indeed. An isosceles trapezium would be cyclic, but not in general. Not all trapezium or trapezia are cyclic, and yeah, definitely not all quadrilaterals are cyclic. But when it comes to triangles, all triangles are cyclic. You can always draw a circumscribed circle around a triangle. So I just draw an arbitrary. I mean, I won't actually do this, but and actually to work out, construct the circumscribed circle around this triangle, you would actually construct the perpendicular bisectors of each of these lines. And you find that they actually meet in a point, and that is the centre of the circle. So you don't actually need to construct all three. You can just construct two, and that will be the centre of the circle, from which you can then draw the circumscribed circle of this triangle. And while we're on the topic, I can talk about inscribed circles. That's a circle inside which will touch all the sides of this triangle. And to do that, you construct the bisectors of the angles. Okay, so the circumscribed will be perpendicular bisectors. Inscribed circle, that should be. C for circle, inscribed circle, that's the bisectors of angles. And you find that bisecting all these angles, that they will also meet in a point, and that's the centre of the circle for a circle that will touch all the sides of these this triangle. Yeah, so I mean, while I'm on the point, I could probably talk about the centroid as well. The centroid possibly is not on the maths syllabus, but it's definitely a type of thing you would meet in physics and so on. So the centroid would actually be acquired by drawing a line from an angle or from a vertex to the central point of the opposite line. So that I've drawn that line in already. Those are the perpendicular bisectors which I drew originally. So that will be the centre of that line. I'll draw a line from the centre of this. I'm sorry for the mess here, but hopefully you can see what I'm driving at. Lines from an angle or a vertex to the centre of the opposite line, or the opposite side. They will also meet in a point. And that would be the centroid. Should I draw that more specifically? So I'm drawing those blue lines in from the vertex to the centre of the opposite side. And they should all meet at a point. And that's the centroid. And sometimes that's called the centre of gravity or the centre of mass. If we were ascribing a mass to this particular object, then this would calculate the centre of gravity. But for a purely geometrical figure, that would be classed as the centroid. But for centre of gravity or centre of mass, that would be the point from which the centre of mass, or the centre of gravity or the centre of mass would be the point from which the mass appears to operate. So I could take an object like that and just replace it with a point with a mass equal to the mass of the original triangle. And that would be, I'd then be able to do calculations, maybe the motions or whatever, or acceleration due to gravity, just by considering that point. Yeah, while I'm again on the topic again, I could probably, again, this is probably not on the syllabus at all, but it's actually worth talking about. The orthocenter. Now, you remember that when I was talking about the heights of these triangles, you can take an arbitrary base and calculate an arbitrary... you can take an arbitrary base and then calculate the corresponding height. And I said, well, the reason it's arbitrary is because I can take any of these three sides to be the base and construct the height from that particular base. And if I was to construct the... have we got a... Let's construct the height here from that line, and the height from this line, and the height from this line. Where am I? That's intersected there. This is probably not going to work out properly but all these heights should actually intersect in a single point as well. Okay, because of my drawing, this has not actually worked very well on here, but take it from me that if you construct those heights from each of those three sides, the heights will intersect, and where they intersect, that's the orthocenter. And what's quite amazing about this is that the orthocenter, the centroid, and the centre of the circumscribed circle all actually lie on a straight line. The centre of the inscribed circle is a bit of an outlier. That does not obey this rule, but interesting point anyway to make while I'm interesting general point to make while I'm on the topic anyway. So yeah, thanks for being with me as always. See you next time.